So you won't be able to buy this drone. That's because you'd have to design the electronics, get the electronic parts and assemble them, program it, 3D print the drone frame, and finally assemble the drone. Oh, and test the drone, which hopefully doesn't go crazy. I've always wanted to make my own flying drone from scratch, but my first attempt only flew for a few seconds. But I hope to change that this time. These 3 parts are what I've been trying to design and make from scratch for over 5 months. The first is the electronic speed controller, aka an ESC. We'll need 4 of these total. It needs to be able to spin a brushless DC motor with a propeller attached, at whatever speed it is told to spin at. This is of course what powers the drone into the air. Next is the flight controller. It'll have sensors that allow it to know its orientation and its altitude. It'll use that data to do lots, and I mean lots, of computations, to then tell the ESCs to spin the motors at just the right speeds. And finally, we have the chassis, to hold everything together. It's a lot more complicated than it looks, a lesson that I had to learn during the project, unfortunately. These 3 main components need to work in tight synchrony with each other, so that we can achieve stable flight for the drone. So I decided to try and tackle the ESC first, because they're just so interesting. I mean, you see this thing with a lot of electronics, and it spins this brushless DC motor like magic. If I want to design an ESC, I'll need to learn the magic behind the brushless DC motor. If you look inside this brushless DC motor, you'll find a ring of magnets attached to the outer housing, which spins around a ring of coils. Let's use a simplified model with only 3 coils and 2 magnets. The magnets on the outside are placed with alternating directions. The coils are connected in a Y configuration, meaning there is a common connection shared between the 3 coils. The other ends of each coil are connected to wires. If we had a higher voltage on one end and lower voltage on another, we can allow something called electric current to flow, aka electricity, through 2 coils. This makes both coils act as a magnet. We can represent the coil magnets, so to speak, as one resultant magnet that combines their directions. Now we can see how the outer magnets would spin, with opposite poles attracting each other. We can pass electric current in a specific order and direction through the coils to make the magnets spin continuously. I've labeled the coils A, B, and C to keep track of where electric current goes in or out in each step. After 6 unique steps, we can repeat it again to spin continuously. The spinning magnets cause a voltage on the unpowered coil. That voltage can be used to know when to go to the next step in rotation. So, at the heart of motors is magnetism, which honestly at this point we can call magitism because it's basically magic at this point. So we have an idea of how a brushless DC motor can spin. The thing that actually makes that happen is the ESC. There are only 3 relevant parts to spin a brushless DC motor: the microcontroller, which coordinates everything, the phase drivers, which applies the voltage to allow electric current to flow through the coils, and the resistor array to allow the microcontroller to know when to move to the next step in rotation. The microcontroller turns MOSFETs on or off using a voltage signal with the help of gate drivers to make the signal larger to switch the MOSFET effectively. When the MOSFETs are off, they act as an open switch, disconnecting the top from the bottom. When they turn on because of a voltage signal applied at their gate, they connect the top and the bottom, allowing electric current to flow. The resistor array produces an average voltage of the 3 coils. When the voltage of the unpowered coil crosses the average level, we'd know to switch at around that time. To vary the rotational speed of the brushless DC motor, we use a technique called pulse width modulation. If we turn a signal on for a percentage of time, then we can change the average voltage of that signal. Use that on the MOSFETs, and we can vary the amount of current through the coils, changing the speed. And hopefully you can start to see how an ESC and a brushless DC motor work together. With that theory in mind, I gained enough confidence to make it real. It's best to make an inexpensive prototype to test it out, so I use something called a perf board, which allows me to connect electronic components together using a soldering iron and some solder. Lots of soldering later, we have this monstrosity. The microcontroller is an Arduino Nano that I plop in for this prototype. Let's power it up to see if it's alive. Oh, it turns on. I tested the power output, and fortunately it turns on the LED. Here we go. Yes! So it does a light up, which means the MOSFETs are working. Naturally, I wanted to test with a brushless DC motor next. So I made the microcontroller run through the 6 steps to spin a brushless DC motor, without detecting when to move to the next step in rotation. Let's see if I can do it. Forgetting to program an entire phase is not going to help. So hopefully now it's actually going to do something. Send a quick prayer. Here we go. Oh, did you see that? It literally spun. Yo. The ESC can spin a brushless DC motor haphazardly without any voltage feedback, so let's try it with feedback. If both parts work, then we'll have a proper spinning brushless DC motor. Long story short, I concluded that the sensing of when to go to the next step and powering the coils with the MOSFETs wouldn't work together. So I took a gamble. I ended this prototype and decided to make it into a PCB. I figured I had the right design, but the soldering workmanship and electrical noise isolation was not there. Both could be solved with a PCB. PCB design is pretty fun. After you have your schematic, you find yourself playing a little game of connect the dots. Obviously, it's a bit more complicated than that because you need to be conscious of how one part of the circuit can affect the other through electromagnetism, for example. After finishing the design, I used this button in the PCB design software KiCad to send in my design to PCBWay. The design is a 4-layer PCB, so I selected that option, and oh, white looks cool as well, so I selected that option. Every other option looks fine, so then I just make the order and wait for the package. Thanks PCBWay for sponsoring this video, because being stuck with this would have killed the project. With the electronics delivered, I started assembling. This chip right here is the microcontroller. I load bootloader firmware and programs through soldered wires. Okay, so this thing actually does work. Our little computer on this board is alive and it's counting up by 1 into forever, basically. So there's nothing right now until I spin the motor very. Look at that. It works. We can see that it detects when to move on to the next step. But will it work together with the components that power the coils and spin the motor? Yeah, that's pretty much what I expected. Looks like I made the wrong gamble with this PCB. But then, you won't believe what I just found out. I'm just gonna show you. Fast enough, then we're good. If I do it too slowly, then it'll just keep doing that. But look at that. Just a casual 1.5 months of work later, and it works. Turns out I just didn't upload the right code at the time. Yeah, that's pretty stupid. But thank you to Greatscott's and Electronoobs videos on ESCs and brushless DC motors, and countless online articles to help me get to this point. So we can power motors, but now we need to control them. As the saying goes, power is nothing without control, which is why we need a flight controller. But how does it actually control the ESC and provide the right inputs for stable flight? Well, it all starts with the inertial measurement unit, an IMU. Now, these things are very cool because they're micro electromechanical systems, MEMS for short. This means that inside of this tiny chip, there are moving parts used to measure acceleration as well as how fast it's rotating, aka angular velocity. It can measure acceleration by using very tiny springs attached to a mass, and when we start to move and accelerate to the right, for example, the mass lurches towards the left because of inertia, pushing these edges closer together. Using something called a capacitor, we can create a voltage that changes in relation to acceleration, which can be measured to give us an acceleration reading. We call all of this an accelerometer. There are 3 of them on an IMU, one for each dimension. To measure how fast we're rotating, we use something called a gyroscope, which has a mass that vibrates up and down on a spring setup. Turns out, if we spin the IMU, the mass vibrates side to side as well. And again, we use capacitors, which leads to voltage being measured, which correlates to angular velocity, or in other words, how fast we're spinning. An IMU would have 3 gyros, one for each dimension. And that is an accelerometer and gyroscope in a nutshell, making up the sensors of an IMU. Man, MEMS sensors are so cool, aren't they? It would be pretty awkward if you guys didn't find that interesting. We can know the acceleration and how fast we're spinning, but to get our tilt angle, we can either use trigonometry on the accelerometer data to get an angle, or multiply each gyroscope reading, which is in degrees per second, by time in seconds, since the last reading. However, accelerometer readings jitter around the real angle, while gyroscope readings start to drift away from the real angle, but don't jitter as much. Well, how about we use both? 2 is better than 1, and we can combine the 2 sensor readings with something called a Kalman filter. It's basically a math algorithm that can be used to combine things like sensor data so that the result is a better estimate of what we want. The magic behind it is essentially adding a percentage of each sensor reading together. If the accelerometer is doing something crazy or unreasonable, but the gyro stays stable, we trust the gyro more and the final estimate leans toward it. If the gyro starts drifting or acting weird, we trust the accelerometer more. It's kind of like agreeing in a friend group. You would put more weight on the reasonable person. It's a beautiful system that allows the whole to be worth more than the sum of its parts. So that's the IMU. Next to that is the ESP32 microcontroller. It'll do the computations and hopefully give us the right output to the ESCs to spin the motors at just the right speeds. Then we have the distance sensor down here, which shoots a beam of infrared light, which in reality is invisible to the human eye, and measures the distance with this equation. Basically using the time it takes for light to travel and the speed of light itself to calculate the distance. This is called a time of flight sensor because it uses the time it takes for the light to fly to and from the target. This could be useful later for something like hovering at a certain height. The rest of the flight controller is just an antenna to receive controller inputs, some power electronics to provide the right voltages to components, and USB circuitry to enable us to upload some code, among other things. Now we just need to put all of that onto a PCB, which PCBWay will once again make for us. Finally, I can test to see if the board can come to life using a very simple test.
Yes! Yes! Let's go! Let's go. Look at that.
Fortunately, this board can count and very fast, demonstrating it's alive and doing computations. Next, I solder on the through-hole components, which are parts that have pins that go through the board, requiring a soldering iron to assemble instead of a heat bed. Let's put the drone's nervous system to the test, using the flight controller to provide outputs to an ESC using my DIY controller for wireless control. And I was absolutely mesmerized by the fact that transmitting a signal by radio frequencies to a flight controller to control an ESC to make the motor spin actually worked. I probably spent like 10 minutes playing with this. So one ESC works well, and I decided to make 3 more. Pretty much more of the same, except more satisfying with multiple boards being soldered at once. I mean, look at all the orderly components being soldered at the same time. We now have 2 out of the 3 main parts of the drone. The last one should be easy. Well, unfortunately, it was much harder than expected. With some shimmying around and brainstorming, I came up with this setup, with the flight controller in the center mounted with 2 bolts, with a hole for the time of flight distance sensor. Then the ESCs are mounted between the motors and the flight controller. The battery would be mounted above everything, but as low as possible to help with stability. The chassis is printed in carbon fiber infused PETG, aka PETGCF, for impact resistance. I had to change out the nozzle in my printer to print that, but it wasn't too hard of a change. Now, where everything comes together. This is where it starts to feel like adult Legos because you take part in the therapeutic activity of assembly without too much thought. Now, did I put any thought into the vibrational characteristics of the mechanical design at all? No. This will bite me in the butt later. For now, we just run some tests on the electronics. One of the ESCs seemed to get stuck, and after some close inspection, you can see 2 pins of the microcontroller on that ESC are merged together. It's a solder bridge, and it's not good. A bit of resoldering should fix that. Here we go. That one's good. That one's good. That one's good. Yes. Now, one day my sister's fiance came in and suggested using clips to keep the batteries in place, rather than just using bolts to press against the battery. It seemed like a reasonable idea, so I designed those clips, 3D printed them, and it seemed to work well after iterating on the exact size. I also added a hook of sorts to hold down the battery wires in place. With the full drone assembled, I can focus on the flight controller program. And boy, was this involved. There's an issue of speed. IMU sensors on a drone need to update very fast to react to changes in orientation. This is a timed test with only IMU sensor data, and this is with both IMU and time of flight distance sensor data, which likely isn't fast enough. The reason for this is because the time of flight distance sensor takes around 20 to 50 milliseconds to take a distance measurement, and then after that we can go back to getting IMU data. So what's the solution? Well, for now, we just take the distance measurements less frequently and to reduce the timing budget for the distance sensor to a minimum of 20 milliseconds. Unfortunately, that decreases its range. But now, the IMU measurements are technically more consistent on average with that trade-off. All this results in timings of around 2 milliseconds for about 4 times, and then we hit the 25 millisecond measurement block. This is about 140 Hz on average, or in other words, updating every 7 milliseconds. But after some research, drone flight controllers need to update their IMU readings at around 500 Hz or more, which means that our 140 Hz won't cut it. With a lot of brainstorming, I couldn't figure out a way to improve that, so I chucked the code into ChatGPT, and it showed me a way to use non-blocking measurements. Right now, the distance sensor is blocking, and that means that once we start a measurement, the ESP32 microcontroller will literally wait 20 or so milliseconds until the measurement is finished. But just like how you'd cook something in the oven for 30 minutes, you wouldn't sit there waiting for it to finish the entire time, unless you're easily entertained. You'd likely do something else in the meantime and periodically check if it's done. A non-blocking measurement is the same. The ESP32 requests the distance sensor to start measuring and then goes on to do other stuff, like taking IMU readings and not crashing the drone. We occasionally check on the distance sensor to see if the measurement is ready or not. This way, we get distance sensor readings at around 20 Hz and IMU readings at around 450 Hz rather than the measly 140. With that figured out, I implemented some basic flight control responses and used the Wi-Fi capability of the ESP32 microcontroller to display some info on the dashboard. I also tidied up the wiring and was able to display battery voltage readings on my controller. And no, we don't have like 100 volts in our battery. I just didn't have enough space to fit a decimal point. Okay, look, I know that a decimal point is just a dot, but the software library that I'm using makes it much larger than it needs to be, so it just kind of shoves a number off to the side into the shadow realm of LED matrices or whatever. I'm getting very close to being able to test this drone with all systems at once. I was afraid of all the things that could go wrong, but sometimes you just need to get started. So I put on the props and started testing the drone on a tripod stand. Okay. Ooh. Dang, that's powerful. Okay. I really don't want to do this, but... Oh my goodness. The drone is able to at least attempt to level itself with some tuning. Yo! Oh my. But that's not quite there yet. What I'm doing on this dashboard is changing some values for something called a cascaded PID control algorithm. Cascaded PID control in my case has 2 parts. One that focuses on the drone's angle itself, which is the outer loop, and one for the angular speed. aka how fast we are spinning in degrees per second. Let's focus on how to control how fast we are spinning first, which is the inner loop of the cascaded PID. The P stands for proportional. The further away we are from our desired rotational speed, the more motor power we request to get to that speed. I is the integral. If it's taking us too long to get to the desired rotational speed, even with the P term, we add more motor power over time. D is the derivative. If we are overshooting too much, we take away motor power in relation to how fast our rotational speed is changing, creating a sort of friction to the system. The thing that controls which angle to rotate to is the outer loop, which only has the P term. So if we want to level the drone, aka 0 degrees tilt, and we are getting further away from that goal, the outer loop will request the inner loop with a faster rotation speed proportionally. All this is good, but for the next 3 days, I tried tuning this thing on strings and trying to outright fly it unrestricted after knowing it won't kill me. But finding the right values for the outer and inner cascade PID loops seemed impossible. There was a lot of brainstorming, but I realized that maybe it isn't software and algorithms. This is where thinking that a drone chassis is a simple design bites you in the butt. Because if you take a look at this test, you'll clearly see how floppy the drone frame is. That can't be good, because one wobble causes a chain reaction, confusing the flight controller. The solution for that would be to make a stiffer chassis, which I did with increasing thickness, a new arm design, and printing with the most stiff material on hand, carbon fiber infused PLA, aka PLA-CF. It's more stiff, but more brittle than the original PETG CF. After assembling the drone with this chassis, the new one proved to be much stiffer under testing. At this point, it would make more sense for the drone to fly, but it doesn't fly. This is where we enter into a world where we humans can't see the problems, but the electronics and software can see it clearly. To see what's wrong, I used this testing rig, which is a fixed tripod with a drone mounted on it. Then we send data through USB. With no motor spinning, the gyro data says that we could be spinning anywhere between 0.2 and negative 0.2 degrees per second on each axis. But turn the motors on, and it'll say something on the order of 20 to 30 degrees per second. Doesn't make sense because the drone is strapped down and not moving at all. So what's the reason for this? Well, the vibrating mass used for both the accelerometer and gyroscope can give us false readings on our angle or how fast we are spinning. That is because any vibration will disturb the delicate mass and spring mechanisms of both the gyro and accelerometer. And now begins the journey of trying to get rid of bad vibes and tuning out the ones that get through. There are two ways we could deal with this vibration issue. We can outright remove the source of the vibrations by changing the drone itself, looking at the things that can come loose, vibrate, shake, and whatnot, or we can use software to tune out the vibrations. So this whole time I was basically passing bad data into the cascaded PID controller, and that means that bad input means bad output. And yeah, that's pretty much how the cascaded PID feels right now. I chose the software route first. Now, the vibrations can happen at different frequencies. What this means is that a vibration that happens slowly is lower frequency, while something that happens rapidly would be higher frequency. The real rotation and movement of the drone would be lower frequency, which would be around 0 to 100 Hz. This is the good gyro data, assuming no other vibrations exist. But what if there is a vibration at 120 Hz? This will contaminate the good gyro data in the 0 to 100 Hz range with bad gyro noise. Fortunately, there's something called a low-pass filter. It can greatly reduce the influence of certain data happening above a frequency range. 0 decibels means 100% of the data is kept, and -6 decibels is about 50%, and so on. We don't want to keep the 120 Hz, so we move the cutoff frequency near there. And now we keep the correct data that happens below 100 Hz without the 120 Hz noise interfering. A low-pass filter in software simply just combines some part of the old data with some part of the new data. A low-pass filter that filters almost everything but the lowest of frequencies would combine a very large part of the old data with a small sliver of the new data. So I tested this out on the drone, and we can see the use of low-pass filters with lower and lower frequency cutoffs, which makes the data less and less noisy. But weirdly, we need to lower the cutoff frequency to 30 Hz to get less noisy, but still unacceptable data. We're basically filtering out everything at this point, including the good data, which in our case is from 0 to 100 Hz. We'll need to look for something better. Another filter is a notch filter, which targets a specific frequency range to filter out, instead of everything above a cutoff number. This is useful because many things produce a large vibration in a small frequency range, and in the case of drones, motors are like that. But we'll need to know precisely what frequency that vibration is at. So I programmed in a fast Fourier transform, which essentially tells us the strength of each frequency. There's a lot that goes into a fast Fourier transform, so I won't go beyond this short explanation. Plotting the data, it says the strongest frequency is around 60 Hz, which could be from the motor vibrations. Would be pretty cool if the notch filter can follow the frequency that the fast Fourier transform detects as the strongest, so that the filter can always hunt down the motor noise, which changes as the motor speed changes. Well, that's exactly what I did, creating a dynamic notch filter. Alright, it's Christmas Eve, and I was putting my hopes in these two filters. Unfortunately, there is no Christmas miracle here. At this point, we are in a dilemma. We either filter out noise in the 0 to 100 Hz range, getting rid of both good and bad data, or we leave them be and have both the good and bad data coexisting. Both result in pretty bad gyro data, unusable for the cascaded PID control. Filtering only really works if the noise and the good data that we want are actually separated in different frequencies. Software can't change the laws of physics, so we'll need to change the hardware to work with the physics. And there's a lot I was missing in the hardware that I didn't think about. First off, the flight controller is directly bolted to the chassis, meaning that any vibration on the chassis would be felt by the flight controller. But second, I don't know what I was thinking when I thought that 2 bolts on one side was good enough to mount a flight controller. It was likely something along the lines of, I'm too lazy to find more space on this PCB for more holes and something like that. Well, now I have to work extra hard to fix the vibration issue. So the solution is to use neoprene rubber between the flight controller and the chassis to dampen the vibrations. It's kind of like a mechanical filter. The issue of 2 bolts, which are both on one side of the flight controller, means that it is also now a cantilever, or in other words, it's hanging on one side. The flight controller will now vibrate like those springy door stoppers on a small scale, which is definitely seen by the IMU's gyroscope and accelerometer. So I used neoprene rubber on the side of the battery brackets to add resistance to the swinging motion of the flight controller. I also decided to put neoprene rubber directly below ESCs to reduce any vibrations that they could cause, since zip tie mounting can cause shaking. Now, when we compare the soft mounting to no soft mounting, we can see some improvement. The thing is, there are more cantilevers, like the IMU board itself. It's mounted on one side by pin headers for electrical connections, but the other side is left hanging. So I designed a brace that should be pretty rigid, which should bolt to the holes in the IMU board as well as the holes on the flight controller. The brace is PLACF, which is rigid so that it won't act as a spring, keeping the IMU from wobbling back and forth. And yet another cantilever is the very long antenna sticking out. I replaced that with a shorter, lighter non-antenna version. I also decided to make sure the flight controller doesn't start swinging by adding actual supports under the flight controller with a new chassis design. And the gyrographs don't lie. These hardware improvements definitely allow us to lessen the source of the noise itself, rather than just trying to mask it through software filtering. When the drone is not tied down, we can pretty clearly see where the graph is going due to the noise reductions. So when I was doing these tests, I noticed that the motors cut out sometimes, due to wires being bent and pulled a bit too hard. Some wire and new solder replacements should do the trick. The drone seems to fly a bit better, but still not how it should. It's hard to stay in one place as I have to be very focused on controlling the drone with my DIY controller. I assumed it was the ESCs, so I replaced those with ones you'd buy on Amazon. Turns out, one motor still had some trouble spinning, so I also replaced all of my motors, and well, this project is starting to get even more expensive than it already has at this point. Well, it turns out all of those replacements gave me marginal improvements. This drifting to the side has plagued all of the iterations so far, and yet hardware changes haven't been able to get rid of it. First, I tried improving the software, and basically I was using the same PID tuning values for both roll and pitch axes. But thing is, the drone is not symmetrical, meaning I'll need separate tuning tailored for each axis. This is because a good tune for the pitch axis is likely bad for the roll. I also added an eye term to the outer loop so that the longer we are away from our desired angle, we command the drone to try and rotate faster and faster until we reach the desired angle. I noticed that whenever I put the bolts through holes, I'd have to spin them and thread them into the frame to get them through. This means that the bolts can be crooked and can bend parts when tightened. Why did I think that this was okay at the time? I don't know. Probably it's because I wasn't thinking about how big the small issues could be. So I fixed that with as you can see, another print of the chassis. So I was troubleshooting and changing the design and realized that the flight controller had a setting to only send updated commands to the ESC at 50 Hz. So this entire time we had a 500 Hz control system updating every 2 milliseconds just to be bottlenecked and blocked by the ESCs that only receive updates every 20 milliseconds. Put into perspective, that is like touching a hot stove, feeling the pain, but your instincts only kick in to move your hand away after 1.5 seconds rather than a fraction of a second. So I changed that setting in a heartbeat. And would you look at that? The drone flies much better. Less wobble and more control. I once again bought a third set of new motors on Amazon as I had some crashes with the second set. But then I noticed these divots on all of the frames. That's not in the design, and then I realized the spinning shafts of the motors were digging into the frame. Wait a minute, do all drone frames have motor holes for motor mounting? Oh, yeah, they do. Well, time to add those holes and reassemble for the, 7th time or so? Guys, I think we got this in the bag. I mean, yeah, sure, there were some stupid mistakes, but we're here now. I've basically beaten myself 1 year ago. This is amazing. Now, all I need to do is utilize some other features to lock this drone in. One is using trim, which essentially forces the drone to tilt at a set angle from the desired angle to account for some drift that can be caused by thrust imbalances due to motors not being perfect. Now, I didn't use my DIY ESC on the final drone, but I understand how it works and how it's used on a drone. Also, it kind of worked before on the previous iterations, so it's also better to be safe than to have the drone careening towards me randomly if the motor cuts out or something. It's been 1 year since my first drone, which failed at sustained flight, but the fall of the first allowed the second to rise. And thanks to the many suggestions you guys have made, the second drone I ever made works. Now, I used to think that being able to create a flying drone from scratch would be impossible, but as I kept going and I kept digging deeper, it felt more and more possible and even easy at times. Okay, maybe not easy. It did take me 5 focused months of work, but it felt like it was actually becoming real. On a humorous note, though, something as seemingly simple as a fly likely has better flight control, autonomy, reproductive capabilities, and more than any drone humanity can make. And then you look at humans and then it's like, how is that even possible? And because I'm Catholic, being able to create this drone has actually made me realize just how much effort God put into making me and you and all of us. I've gone over some pretty big concepts in this video, so let me know in the comments what things you'd like me to talk more about from this video. But I do plan on making a deep dive video on the ESC design.